This is Projectile Motion 2, the human cannonball, motion at an angle, a worked example. In this example, we now have a cannon in the picture, right over here. And the cannon, in this case, is shooting a human projectile. And that human really cares about being caught by a net. That's something that's important if you're being shot out of a cannon. So what he wants to know is how far from the cannon is the net going to get placed. So he's really interested in distance. Okay, that's also called the range. So he's interested in the range of the cannon. The other thing that's of interest to people is how high does the guy actually get into the sky? How high up does the projectile take him? And of course, that happens halfway through the path, and that would be our dy max. We're going to have some initial velocity coming out of that cannon, and that velocity is going to be at some angle. We're going to be interested in how far, the range of it, and also we're going to be interested in what is his maximum height. Note that maximum height happens at the halfway point, so t1/2, or as I like to say it, t on the way up. David Smith Jr. is fired out of a cannon at 60 miles per hour, 26.8 meters per second, with an angle of 72 degrees. How far away was the net from the cannon, assuming he was caught? What was the maximum height he reached? So we have two unknowns here. We're going to tackle them one at a time. And just like before we start tackling unknowns, or tackling the problem period, we're going to draw a picture of what we've got. So we have some cannon thing going off at an angle, and it's ejecting a velocity. That velocity, that initial velocity, is equal to 26.8 meters per second. David Smith Jr. is flying through the air, and he's going to end up. And the assumption is that he's going to end up at the same level as a cannon, and that allows us to say di in the y direction is still 0. We also know this angle of 72 degrees, and we know this initial velocity has an x component and a y component. Not only do we know that it has an x and a y component, we also know how to find out what those x and y components are, thanks to all of our vector work. Thanks to our vector notations, we know that the y component of any vector is just that vector times the sine of theta. And likewise, the x component of any vector is just equal to that vector times the cosine of theta. So we're going to use that information to find the x and y components of that initial velocity. Like before, we know the acceleration on the x side is 0. We know the acceleration on the y side is negative 9.8 meters per second squared. Like before, di on the y side equals 0. Like before, because and only because acceleration equals 0, we can say that we can use that easy equation on the x side of v equals d over t. We also want to go ahead and get our components right away. So v I y is equal to 26.8 meters per second times the sine of 72 degrees. v I x is equal to 26.8 meters per second times the cosine of 72 degrees. So we know that VIY is equal to 25.49 meters per second, and VIX is equal to 8.28 meters per second. We can't confuse those. We have to keep the initial y velocity on the y side and the initial x velocity on the x side. The only thing that's common between the two sides is t equals t. And we're going to find something interesting about that. In the past, we used df equals di plus vit plus 1/2 at squared. And we used that because we had a value for df that we could use in the equation. But we don't have a value for df anymore. In fact, that's going to be one of our unknowns. So how do we do this? This equation is not going to work. We're going to have to say, no, no, you're no good for us. We can't use you. So we have a blank slate. What equation do we have? What else do we know? Well, we know, going back to our picture, that the very top of this path, Vy equals 0. So now we have two values for Vy. We have a value here at the very beginning, and we have a value right at the middle. So if we have two values for Vy, that opens up the door to different equations that we can use. Consider the simple equation Vf equals Vi plus At. We have two values for V. We have the acceleration. This will work. As long as we remember, if we're going to use Vf equals 0, that's true when t is only halfway or on the way up. So when we use that value, we're just going to find the halfway point for t. So let's go ahead and do it. We've got 0 equals 25.49 plus a negative 9.8 times t. Oh, this is easy. Our t is 2.6 seconds. But remember, this is the time it takes to get up to the top. We're concerned about, in our first unknown, how far does he go all the way to the end? He wants that net there when he hits the ground. So we're going to have to double the t. So this relationship of t equals t, we've got to be careful with, because in this case, over on this side, we want to know not t up, but t up and back down. And that, of course, is just the other one doubled, or 5.2 seconds. Now we've got a t, we've got a velocity, we can find the distance traveled. As a reminder, we're hunting for dx, the x range. We're on the x side. That means we're only concerned about the initial x velocity, not the y, but the x. And it means that we have to be careful. We want the time both up and down. So I just put those subscripts in to remind me what numbers I'm going to be using. So d is equal to 8.28 times 5.2. So that gives us our range, dx, of 43.07 meters. That's how far he travels the full time, hitting back on the ground at the same level that the cannon ejected him from. Now let's take a look at that second unknown. What was the maximum height he reached? Well, recall that his maximum height is this distance right here. But that distance right there is at t1/2. So we can use this time over here to find it. You can do this any number of ways. I like using Vf squared equals Vi squared plus 2AD. But there's obviously other things that we could do here. I'm just going to go ahead and do this. I've got a 0 Vf, because that's at the very top of his path. My Vi, remember I'm working with the y, so I'm going to have the y initial velocity. So that's going to be 25.49. I'm working with the y side, so my acceleration is negative 9.8. And remember, I'm going to find a y distance. Also, don't forget to square that initial velocity. And we get for our y distance, our maximum height halfway through, 33.15 meters. And we've solved the problem. Thank you very much for your time.